All right, here's our last example. So say we've got a rock of mass 1 kilogram and it's attached to a string of length 0.5 meters. So R equals 0.5 meters, and we've got the rock up here, 1 kilogram. All right, and the string snaps at a tension equals 75 newtons is our snap. That's when the string all of a sudden will snap. Okay, so we very, very slowly increase the speed of the rock traveling in a vertical circle until the string snaps on us. So it starts off going very slowly, and then faster, and then faster, and then faster, and faster, and faster, snap. All of a sudden it snaps. First, let's think about what point on the circle will the string snap. So where does it snap? So let's do a quick free body diagram. So at the top, we've got mg, right? And let's say for ease, that just understanding it graphically, we have to have a full length that's equal to the length of the radius. So in this case, we put these two vectors together. We've got some tension pulling into the center, some gravity pulling into the center when it's at the top, right? Well, when it's at the side, we've got gravity not really having an effect because it's going perpendicular, so it's not doing much to us right now, but we've still got that tension. So now the tension has to go all the way in. So clearly when you're on the side, you're going to have more tension than when you're at the top. Well, what happens when you're at the bottom? Well, now we've got mg pulling down, but we've also got to have a tension that's able to make up for mg so we can still maintain the same centripetal force. So to maintain the same centripetal force at the top, gravity is working with us. It means we need less tension in our string. When we're on the side, gravity doesn't have any effect. It means that we need just the same amount of tension that we need as our centripetal force. When we're at the very bottom, gravity is going to work the most against us, and so the tension is going to be the maximum. So string snaps at bottom. So string snaps at bottom of circle because that's when gravity and tension are going to be butting heads. The tension will have to be the biggest because that's when gravity is working against us. So at what speed will it have to go? So now we have that centripetal force is equal to the net force, right? The sum of the things, because centripetal force is only created from other things. So the centripetal force is equal to the net of the forces. What forces are acting on the rock? Well, we've got gravity pointing down, and we've got the tension pointing up. So in this case, we'll make up positive. So we've got tension minus mg. So that's what the net forces are. And then centripetal force is going to be mv squared, speed squared, absolute value of v, over r. All right, we know what pretty much all these numbers are, except what's tension? Well, we're looking at the instant of snapping because we very, very slowly sped up to this. Because if we'd sped up to it suddenly, we might have accidentally put on a 75 Newton tension at a different spot. That's why we had to speed up slowly so we could be sure that it would snap at the bottom. So we've got that the tension's 75, and we can now start subbing things in. So at the instant of snapping, the tension's 75. We know what the mass is. We know what gravity is. We know what the radius is. We know what the mass is. Now it's just up to us to figure out what v squared is. So v squared m over r equals 75 minus 1 times 9.8, which equals, So 75 minus 1 times 9.8. We move things around some more. We get v squared, the absolute value of v squared, speed squared, is equal to the radius. What's the radius? The radius is half a meter. 0.5 times 75 minus 1.98 divided by the mass. What's the mass? Well, the mass is just equal to 1, so we can forget about it being on the bottom. And then we take the square root of both sides, and we get the square root of, we punch that other number into our calculator, and we've got 32.6. Once we take its square root, we see that the speed of snapping is going to be 5.71 meters per second. Once we get faster than 5.71 meters per second, we'll snap at the bottom of our circle. As soon as we get to 5.71 meters per second and the rock passes through the bottom, that's the just enough tension to create a 75 Newton pull in the string and snap it. All right, hope everything made sense. Hope you learned a lot, and I hope you enjoyed it. We'll see you again at Educator.com later. Thanks.